Paul. This is really a great honor to have you here today. And Dr. Jerzak, I will just the card to introduce him, and then I'll just if this is your first time, join our Colloquium. And I'll let you briefly let you know that this is our fourth season since 2020, right, Paul? And then we're
2020. Yeah,
great
that's
honor.
right.
Yeah, we're very honored to have this opportunity and to invite many top-notch scholars and to join us to share their firsthand research and share with us the methodologies in political science, social sciences. So, welcome. Welcome aboard. And before we started, I just want to let you know that this initiative is sponsored both by NCHU, Chongqing University, National Chongqing University in Taiwan, and the UPD. So it's been a pleasure that I worked with Dr. Ho, and all the guests since 2020. So please stay tuned, and then we still have a few more presentation and the speeches in the coming weeks. I hope everyone we enjoyed today's talk and given by Dr. Kama Jerzak. All right.
Perfect. Thank
All
you.
all right. Allow me to start here to introduce our speaker. And it is really my pleasure and my honor to have Professor Connor Jerzak and to be our speaker tonight. And Dr. Jerzak received his master's in statistics and PhD in government from Harvard University. So he was advised by Kosuke Imai and Gary King and Xiang Zhou. And Dr. Imai was our speaker in our previous series. And during his study as a graduate student, he also worked as an intern at Adobe Research in San Jose, California, within the Coast Velasquez. And in the year between 2021 and 22, Dr. Jerzak did a one-year postdoc with Adele Daoud and the AI and Global Development Lab at Linköping University in Sweden, while serving as a visiting scholar in the program on governance and local government. And that was at the University of Gothenburg. Since 2022, uh, he has served at the University of Texas at Austin as an assistant professor in the Department of Government. His research has appeared in or is forthcoming in peer review machine learning, economics, political science venues. And he will be teaching next spring in Harvard University. So we're really pleased and we have the privilege to have him talk to us and at Data Analytics Colloquium. And his topic tonight is selecting optimal candidate profiles in adversarial environments using conjoint analysis. And without further ado, allow me to introduce Professor Connor Jerzak. All yours.
Thank you very much, Carl, and thank you, Peter. Thank you both for organizing this great series. And also thank you to those in the audience for taking time to be here with us today. So today I'm going to present some new research, and definitely looking forward to any questions or comments you might have. And because we have a bit of time today, I think around 1 hour and 50 minutes. I'll first present the material, and then we'll leave definitely the second half, about an hour or even an hour and 10 minutes for a bit of a tutorial, as well as any questions that you all might have. It would be great to talk through that. So I can't see the hands or the screen of other people in the room. So if you do have a question while we're going through the presentation, definitely let me know and interject through the audio. So without further delay, let me start by just showing some data points. So this is a data analytics colloquium, and let's just present some data on political candidates. So this is something that you might see in news reports, or this is something that you might see in, in the public press, data on different political candidates. For example, in this case, Trump and Clinton, and we might have information in these surveys about the percent of voters or the percent of likely voters who think that one of the candidates has, more of an would be better for, X or for Y. So in this case, 34% of voters stated that Clinton would be better at being honest and straightforward, whereas a different number of voters said the same for Trump. So we see that there are these different attributes of these two candidates, Trump and Clinton, and these attributes, they voters feel certain ways about certain of these attributes. And, these attributes can be quite detailed. So here we have issues on big picture things like dealing with the economy, like appointing Supreme Court justices, like being a good commander in chief. So these are sort of big picture policies that these two candidates might take on. But there can be much more fine-grained policy distinctions between the candidates as well. So here are distinctions between Clinton and Trump with regard to individual taxes, income taxes, capital gains tax, corporate taxes. All of these fine-grained policy positions together make these candidates who they are. And the big question that we're going to ask, right, through this introduction is what makes a political candidate more preferable in the context of competition and also in the context of institutional constraints. So what we talked about in the previous slides when we were looking at those, those favorability scores on those different sort of attributes of the candidates, those features are somehow combining together to make one candidate more attractive for a given voter and another candidate less attractive for a given voter. So how are we going to understand this, especially in the context of these two important features of the political world? So in the political reality, we have competition between parties, and we also have institutional constraints. Politics doesn't occur in a vacuum, and we want to, in the project, think a little bit about how to answer questions that are being posed here. So the big picture question that will be motivating us today will be these questions. The methods that we'll discuss aren't specific to these methods, but actually might be able to speak to a larger class of phenomenon related to competition and related to adversarial kind of dynamics, which we'll discuss. We'll go through that, and it would be great to have a discussion with you all about what you think in terms of when you think some of these sort of methods might be applicable to some of the things that you're working on. So that's the big picture, but let's dive into some of the details about how we might start towards answering this question. And one way that scholars of politics have tried to answer questions like this is through something called the force choice conjoint design. Some of you may be familiar with this. Some of you might not be familiar with this. I'm not sure what the backgrounds are of the group, but we're going to build things up step by step. So we'll bring everyone along the way. And just to give you some more details about this research design that we're going to be investigating today, this research design is based on a very simple question. And hopefully you all can see, as I'm flipping through these slides, the question that we're going to ask is a simple one. We're going to show potential voters or survey respondents or people like that. We're going to show potential voters two different candidates. One candidate, example here to the left, another candidate, example here to the right. These different candidates will have features like female, like partisanship, like their position on different policies, like their ethnic background, like other personality characteristics. So we're going to show voters two candidates, and all those two candidates will have features that we see here. And on the basis of that, on the basis of this sort of design, we're going to randomize all of these features. So we're going to randomize whether a given hypothetical candidate has, is gender male, gender female, or Republican or Democrat, or cuts taxes or would like to raise taxes. We have all these features, and we're going to show a bunch of respondents, a bunch of hypothetical candidates, where all of the features of these hypothetical candidates have been randomized. So the technical terminology that you may come across is that we're going to randomize we're going to independently randomize each feature. If these features are often known as factors, and we're going to randomize those factors to one of several options or levels. So, for example, for this personality characteristics, compassionate versus strong leadership, that would be an example of a factor or a feature, and the options that this could take on would be a level of that feature. So that's just giving you some background for the terminology, which you may be familiar with, and that's fine. That's why we might be reviewing this. And the interesting thing about this is that if you think about this, we're working with a really high dimensional treatment regime. In the context of some experiments, we have a really simple treatment. For example, a get out the vote campaign, or maybe a survey experiment where we say, let's randomize this this get out the vote campaign, or let's randomize this treatment in my survey experiment where I'm trying to understand the effect of this versus that. That's what we're used to. But in the conjoint experiment setting, we have not just a binary treatment, but we have a high dimensional treatment set where we have all these factors together with all these factor levels, and all of these are combining to generate these high dimensional treatments. And this is going to be important in what we're going to discuss. The fact that this is high dimensional will be relevant to the subsequent discussion, but I wanted to just show you this so that it's in the forefront of your mind when we go through some of the notation, the mathematical notation. If you're not, we'll try to break the notation down as best as we can. If you do still have questions, definitely let me know afterwards, and we can hash through any remaining questions as well. So in the context of this sort of research design, let me talk a little bit about some of the existing methods that have been used, because that's actually going to motivate what we're going to do to try to build on what's been done. And there's been a lot of great work done in this area. So one of the things that often is done with conjoint data, maybe you've actually done this yourself, or maybe in some of the problem sets in your classes, or some of the problem sets in previous classes, you've worked with estimands like this. But one of the crucial estimands for the analysis of conjoint data is something called the average marginal component effect. So this is abbreviated AMCE if you haven't seen it before. And the basic idea behind this is, let's look at one factor at a time, averaging over all of the other factors. So the basic idea here, I have some notation here. It might look intimidating to some of you, but it's actually something that we can break down very simply. What we're ultimately going to do with something like this AMCE is we're going to ask something like, what is the average favorability? So Y here might represent something like favorability. What's the average favorability of a candidate who has, let's say, gender fixed to male compared to gender fixed to female, where we average across all the other possibilities for all the other features. And we're doing that according to the data generating distribution. So there's a bit of terminology there, but the basic idea is, let's just look at all of the hypothetical male candidates against all the hypothetical female candidates, and see which one gets chosen and which one doesn't get chosen. And this generates this average marginal component effect. And there is an extension to interactions, which I should mention too, which is important. And we'll actually refer to that a little bit later on as well. So this is one thing that's been developed in the literature, and we're going to try to put ourselves in dialogue with that. But I want to talk about it now here to give you a lay of the land if you haven't seen this before. The other thing that's been developed in the causality literature is the exploration of heterogeneous treatment effects. So the idea that not everyone is going to respond in the same way to the same candidate. So there's going to be some what we call heterogeneity on the basis of the respondent. So the respondent could be a voter, it could be someone else in your survey experiment, and different people in your survey experiment, different people who are potential voters, they're going to respond differently. And in the context of that, there's been a great deal of work done to look into what, in the context of binary treatments, would be best to do for a person with a given set of characteristics. So the idea there is, if a certain kind of voter really responds well to this treatment, let's give them that treatment if we're trying to maximize the overall number of people who vote, for example. So this is these are some of the things that have been developed in the context of this. So I have some of the details here in terms. If you're into this literature, some of these things might be familiar to you. this notion of an S, a T, an X learner, tree-based methods, causal forests. Those are all things that have been developed primarily in the context of binary treatments and treatment effect heterogeneity. There's also been a great deal of work on these individually optimal treatment rules, as well as some recent work on heterogeneity analyses with conjoint data. So there's a great, these are some of the things that have been developed for analyzing the conjoint data that I just was talking about a moment ago. But in these approaches, they all have their strengths. And what we're trying to do is supplement some of these methods, supplement some of these tools with another set of tools. And we're trying to build on a few of the potential limitations of the existing state of art. So one of the limitations is that these average marginal component-wise effects, we're looking just at one factor at a time. So we're just looking at gender, or maybe we're looking at two factors at a time, gender and ethnicity, or gender and country origin. But in reality, we might care about more complex sorts of interactions. Or in addition, we're averaging over potentially informative variability in the data. And another thing that really we've been looking for and we don't see at this point is the quantification of strategic considerations. Politics, as you know, it doesn't occur in a vacuum. It occurs in a very competitive environment where one group is trying to vie against another group for limited resources. And this is actually a really important part of the political story. And we need to talk more about that in ways that we'll talk about in this discussion. So just to kind of put what's been developed versus what we're trying to do in this paper, we'll talk about it now. So in terms of the contributions of this work, we're going to focus not only on one or two factors at a time, but we're actually going to seek to summarize the role of all of the different factors in the experiment at once. In other words, not looking at just gender or just ethnicity, but looking at all of the features of the candidate at once. And we're going to try to do this in some optimal way to make a statement about what would be the best kind of candidate for potentially the certain kind of voter. And moreover, instead of setting aside these strategic considerations, we're actually going to put those front and center. So we're going to seek to develop ways of specifically and explicitly incorporating strategic dynamics while also discussing institutional constraints and, importantly, propagating uncertainties along the way. So this is really important for doing statistical inference with some of the tools that we're going to develop. And if we have time, at the end, I have some slides which actually go through some of the computational tools that we do in order to propagate these uncertainties so that you might be able to actually use those tools in your research. So we're going to potentially, if there's time, talk a little bit about different sort of computational backends for doing this, which I think will be hopefully informative for you all. So in general, the framework that we're going to discuss today, this optimal stochastic intervention framework, is going to hopefully at least usefully characterize strategic dynamics that are present in the analysis of conjoint data. So this is a big picture of what we're doing in a 30,000-foot point of view. And in the next few slides, we're going to get some details. We're going to put some, we're going to get some additional details to this so that you can see, hopefully what we're doing, and then we can discuss applications or have discussion at the end. So I'm going to move on now to some of the details that motivate this project. And we're going to start from something that you may have seen before. And I should say that this quantity is known as the stochastic intervention, and it's been in the literature for a few years now. And let me try to explain this as clearly as I can to you. So a stochastic intervention, it has a few different building blocks. The first building block is this expected value, the expected value of this outcome. T here is just it's bold. So bold here means it's a vector. So bold T means a vector of different attributes of a political candidate that we're using in this conjoint experiment. So the basic idea here is to look at the average outcome in terms of, let's say, candidate favorability, where we are going to think about assigning those treatments, those attributes of a candidate in a new way with a new distribution. In the experiment that you ran, maybe on MTurk or Facebook, the conjoint experiment that you ran, used one distribution for allocating the features, like if the candidate is male, if the candidate is female. We're going to do something similar to that, but now we're actually going to think of a counterfactual or a hypothetical treatment distribution, which we're going to call pi. So no, it's a new distribution. It wasn't used in the experiment, but we're going to use it to try to come up with a sense for what the average outcome would be under a counterfactual distribution. So the idea here, I hope you're following along, and if you're not, definitely we'll talk about it and hopefully it will become clear. But the idea here is to get a sense for what the average outcome would have been under a new way of assigning the treatments. And there are some good things about this, and one of the good things about this is that we're averaging across all treatment combinations. So here, the nice thing about this stochastic intervention is that we're not just looking at one factor or another factor at a time, like we were doing with the AMCE that we just talked about. Instead, we're actually looking at all of the different aspects of the experiment at once. So that's what we're doing through this counterfactual probability distribution. So this PR of pi is defining a useful model-based summary of this complex treatment process. So these are some strengths, but there's some limitations as well. For example, there's not much guidance for how do we choose a good stochastic intervention. There's a whole range of different possibilities that I could consider. So just to make this very concrete for you, think of this as like a new, this stochastic intervention is like a new distribution for allocating the treatments. So it's almost like a political strategy. What sort of political candidates should I upweight, or what sort of political candidates should I downweight? That's sort of the idea, the intuition behind this stochastic intervention, which sometimes I'll refer to as an SI. So those are some of the strengths, those are some of the limitations. And what we do in this paper is discussing this notion of an optimal stochastic intervention. So this equation down here, don't be intimidated by it. It's the exact same equation we had up here. The only difference now is that we're doing a little bit of optimization to come up with the distribution, that pi, that is going to actually maximize the average outcome under this new counterfactual treatment distribution. So the idea here is, let's take that idea of upweighting or downweighting certain candidate attributes, and let's actually choose that upweighting and downweighting procedure in a way so as to maximize, for example, the favorability of the particular candidate. And the idea there is that this strategy will be useful for summarizing how people respond to different kinds of candidates in a sort of holistic way, not just one feature at a time, but holistically across all the different features. So this is some of the discussion that we'll start with. And the starting point here, so what I just was discussing, it's going to be useful as a starting point, but without any sort of constraints on the problem, the optimal stochastic intervention will actually reduce to the problem of just finding the single best profile, the single best candidate type. So the intuition here is that if we don't put any limitations on our search for that counterfactual weighting distribution, we could just choose, we could just figure out a way to choose the best candidate in some global sense. But remember, these treatments that we're working with in this conjoint design are high dimensional. So we actually have far more treatment combinations than we have numbers of observation. So as a result, a search for the best profile among all of the possibilities is going to be infeasible. So what we're going to do is we're going to add a little bit of regularization. In your data science curriculum, you may have come across lasso or ridge regression.
Mm-hmm. Yeah,
and the idea is similar to that, yes. The idea here is similar to that, but there's a key difference. So here we have
Connor.
Questions, comments.
Sorry to interrupt you. So do we have any assumptions of all these factors or all these features to be orthogonal, or so I think you're going to do the regularization, but at the beginning and the setup, there's no assumption needed for these features, right?
Correct. I guess there are a few sorts of assumptions that we could make, and I'll talk more about but the idea behind the counterfactual treatment distribution is the idea there is that we could upweight and downweight features without limit. So there's no real limit to that. And we're going to talk about ways to introduce limitations to address the problem I just talked about.
Okay.
But in the framework up to now, we haven't really introduced any assumptions yet.
Okay, I'll let you finish the regularization first. All right, then I may have more questions. All right, please go ahead.
Sounds good. And definitely do interrupt. Like I said, I can't see anyone, so just interrupt and we'll talk about it.
Okay.
So the idea there is we need to put constraints on the problem. Otherwise, we're going to need to look across all of the different possibilities, of all these different candidate types, and there are just millions and billions potentially of these different profiles because we have such a high dimensional treatment space. So the idea here is we're going to add a little bit of regularization, and it's similar to ridge, but with a bit of a difference. So in ridge regression, we're trying to minimize the sum of squared errors, and then we add a penalty term for the regression coefficients getting too big in some way. Here we have the objective is similar in spirit, but there's a few differences. One difference is that now we're trying to maximize that average outcome under the new distribution, what we're calling Q of pi. That's the average outcome under the new distribution. So think of it like I'm trying to maximize the favorability for this candidate based on their policy positions. So that's the first part. The second part is a penalty term. It's no longer a penalty term on coefficients in a linear model, but it's a penalty term for the counterfactual distribution, this pi, which is defining that counterfactual probability vector of assigning all of the different different features in a hypothetical way. We're going to penalize if this counterfactual probability vector deviates from the data generating probability vector. So P here is denoting the data generating probability vector. So think of this like, the problem if you have, let's say, two parties, Democrat and Republican, and they're assigned with 0.5 probability, then the entry in P for that would be 0.5, 0.5. And if it made more sense from a strategic perspective to upweigh, Democratic candidates, then the probability would be in pi now, and that might be different. And we're going to penalize things in pi if they get too different from P. So the intuition here, I put a lot of the intuition in gray. So if you want, the intuition here is that we're going to look for a new distribution that's going to maximize the average outcome. The reason we're doing this distributional approach is to overcome the limitations that we had with the AMCE, where we just looked at a factor at a time. And now these new probabilities are going to have a certain constraint on them. And the constraint is that we're going to need that they lie within a certain distance from the data generating probabilities. And we have some analytical discussion of this in the paper. The idea here is that when pi gets really far from P, in other words, when the data generating distributions are really far from the new counterfactual distributions, that's going to really increase the variance of estimation. And that's why we add the penalty in to reduce the variance of estimation. And this is what it's this regularized optimal stochastic intervention that we're going to work with through the rest of the discussion. Does this clarify the previous question, or maybe if I go on, there'll be additional clarification?
Please go on. I think that for those who are familiar with the machine learning literature and materials, and this is coming from the statistical learning, I think materials are learned about the shrinkage and also regularization, and the same goal of reducing the estimation variance, so you can then improve your model by imagine that you're shrinking some coefficient to 0 in order to find how much you can balance between bias and variance. Then, of course, in this case, then the variance being reduced, and in order that you can find out the best model. Yeah. All right, go ahead. This is very smart way of doing that. Yeah.
Yeah, no, great connection. And just to play out the similarities and differences a little bit more, in regression, where the model is a model for the model, whereas here the model is a model for, think of it like a strategy. So pi is, I like to think of it just like a strategy. So it's definitely, there's a similar sort of flavor, and there are a few differences, and we'll hopefully have a chance to further discuss those similarities and differences. But if we continue, so we have in the paper, there are a few different ways of doing this, but the starting point that I wanted to start with, because I think it gives a little bit of intuition, is just with a simple model. We have a generalization of this, in the paper, but I want to start a little bit more. And let's first consider a model for the outcome. So we have two models now. We have the counterfactual model for that strategy, and then we have a model for predicting the outcome in the experiment, whether someone is going to support or not support a given candidate. So if we consider a linear model with interactions, in this case, we're interpreting that as modeling support for a candidate with features bold T as depending on the main features, like whether that candidate is a Democrat or Republican. And we're also going to incorporate all the interactions between the different features in that model for the candidate. So this is it written out. There's a lot of notation with this, but it's actually simpler than it seems. So we have this model for Y of T. Y of T is just, think of that like the favorability for a given candidate with a profile T. And we have this model set up here where we have the main effect term, and we have these interaction effect terms. And we're basically saying, let's summarize the relationship between all of the treatments and all of the favorability responses using this sort of one thing we will do in the paper is we have this closed form optimal variance constrained optimal stochastic intervention. So if we have this sort of model for the outcome, we can, with the closed form, derive the exact optimal stochastic intervention with that regularization term. And this is important because this basically is like a recipe, and the recipe gives you the strategy given the idea here is you have all the conjoint data, you fit this model to it, and then to summarize all of the complex interactions, we use the recipe derived in the paper to get the kind of the optimal strategy from all of the data that we've gotten from the experiment, which you might want to do in order to understand this process better. So it's in the paper. The formula, it involves a little bit of linear algebra, but I think in the appendix we might have some details on it. It has the solution that we derive has a certain computational complexity. So this basically means this is the term here. So this big O term basically means we have this product here, and so LD is the number of levels per factor. So if we have 5 different possibilities for a factor, let's say 5 different ethnicities, then LD in that case would be 5. So the basic idea here is that as the number of factors and as the number of factor levels increases, the closed form solution gets slower and slower to compute, which isn't the end of the world. It's pretty fast and pretty efficient, but that gives you some intuition for what makes the problem easier versus what makes the problem harder. Yeah, so that's what we have there. But some of you may be wondering, especially if you're coming at this from a statistical background, how do we think about statistical inference in the setting? What we've done up to now is related to this idea of estimation. How do we estimate that pi star? How do we estimate that optimal strategy? But the next question is how do we do the next step, which is understanding not only the point estimate but also the confidence intervals. The confidence intervals are going to be important to your research. They're going to be important to the publication process or communicating with policy officials or public officials. And what we do there is we apply something known as the delta method. And this is basically a way of quantifying how uncertainties in the model for the outcome affect the optimal the kind of the policies under that optimal solution in addition to the optimized expected outcome. I have some details on this in the tutorial section if we have time for it. But the basic idea is we have a model for the outcome in this way, and that model implies a certain optimal variance constrained stochastic intervention. So to get standard errors, we can propagate uncertainties from the model through to the optimal using the delta method, which we have a few more details on later on. And I hope this intuition is at least giving you some flavor of how this is coming about. So this is the first starting point. And there are a few loose ends, however. So some of you, there are a few loose ends, and one of the loose ends is that if the regularization is not strong enough, then the estimates may be below 0 or above 1. So that's one constraint. Another issue or another loose end is that we might want to introduce higher order interaction terms, or we might want to add in nonlinear outcome models, so GLMs or other sort of nonlinear outcome models, neural nets, who knows? We could think of a lot of different kind of models for the outcome. So the general method that we're going to discuss here is the method described here. So we're going to model the outcome in some way, and then we're going to compute the regularized optimal stochastic intervention under gradient ascent. So the basic idea here is that instead of deriving a closed form, we're going to use an iterative optimization method for doing the optimization, and we're still going to be able to propagate uncertainties using the delta method to get standard errors, which are really important for the reasons discussed. But we're going to do this using some more, I guess you could say, some more specialized computational tools involving things like automatic differentiation. Because I want to make sure that, you know, if you are interested, that we can talk a little bit about the tutorial material on that. We have some slides that actually walk you through how to do something similar to this in your own projects to try to, you know, empower you in your own research. But the basic idea is that we're going to do an iterative optimization when we can't figure out a closed form solution for those more complex cases, and we're still going to be able to get standard errors using these computational tools such as automatic differentiation, which is going to be important for that discussion, which I'll leave to the tutorial. And this approach here is only really going to be limited by an outcome model variance covariance matrix. So if you're coming at this from a more statistics background, you might know this notion of variance covariance matrix. That's basically a summarization for how all the different parameters in your model for the outcome are, how all those parameters are related to each other in some way in terms of covariances and in terms of variances. So that's a variance covariance matrix, and that's the only requirement that we really need to go through with this approach. This is a little bit abstract for now, but we'll talk about it a bit more in the tutorial, and I think you'll see a little bit more about the details of it. So I want you to, you know, have these tools too, computational tools, to go about your own work. So this is, I guess, like halfway through the discussion. So we've talked a little bit about optimization. We talked a little bit about different strategies, but we haven't talked about the most important part, which is these adversarial dynamics that I introduced this discussion with. You know, we all know what adversarial dynamics look like. They can be they're not pretty, but we need to talk about them. So in most experiments, data are analyzed in a sort of average case manner. So the average marginal component effects, the average marginal interaction effects, we're averaging in some average case way. So the idea here is we're computing marginal quantities, averaging over sources of stochasticity. So those are, maybe that feels like jargon. Just to put it more simply, we look at one thing at a time and average over everything else. That's the intuition. But so one example of this, we can actually write the average case optimal stochastic intervention using forced choice data like so. So up till now, I've only really talked about one candidate at a time. But in reality, we actually don't have just one candidate at a time. We have two candidates who are competing with each other electorally. Or if we were looking at data from, international relations, we might have two parties who are engaged in some kind of conflict. And so in this case, we could think about the following, where In this case, we have this maximization problem, very similar to before, but now we're trying to maximize the probability that candidate A is chosen over candidate B. So that's what this equation is telling us. So this Y now is the utility of candidate A. And if the utility of candidate A is greater than the utility of candidate B, then candidate A wins. That's the idea. And we're basically now in this average case sort of analysis going to optimize the probability, the strategy for A only, averaging over all the different things that B could do. So this is sort of the average case setting that most experimental work is using right at the moment. So here are just a few more details. P again denotes the data generating probabilities. If some of the details aren't clear, or if you want to talk more about them, we can talk about them now, or definitely we can come back to these slides in the Q&A and we can hash over any and all details that you might have questions about. So this is an average case sort of analysis where we're just trying to optimize A. We're not trying to optimize B at all. But in reality, we have competition. We have Group A actually competing against Group B for scarce resources under constraints. So Party A is vying against Party B after they compete in primaries. So there's a way in which this average case analysis isn't respecting the adversarial nature of the real world in that sense. So the main contribution I think that we're trying to make here is to think about how we introduce this notion of competition to conjoint data in some kind of principled way. So what we're going to introduce now is something that has the following intuition. Instead of just looking at candidate A and trying to increase their favorability alone, we're now going to think about a more complex case, but more realistic and hopefully useful case, where candidate A is seeking to maximize their vote share in a second round of voting, while ensuring that their candidate can get there. And candidate B is going to be doing the exact same thing at the exact same time. So think of this in terms of Republicans and Democrats. The Republican Party is trying to choose the best candidates on its side, while the Democrats are doing the exact same thing. But these two parties don't exist in isolation. These two parties exist in a primary system. So if you're not familiar with the U.S. electoral system, there are two stages of the competition. In the first stage, parties compete within that party to then get the opportunity to compete in the second stage against the other party. So first there's inter-party competition, and then there's intra-party competition. And this is something that we quantify with the following. So here we have a min and we have a max. Before we just had a max, now we have a min and a max. And the idea here is that candidate A is trying to win, but candidate B is also trying to win. And this is one way of formalizing that idea. So we have this mini max, this min, one is trying to maximize, the other is trying to minimize, and it's a kind of sequential game theoretic type of framework. So the intuition here is that Republicans are optimizing their candidate, while Democrats are optimizing their candidate. And there's an institutional constraint to this problem, which we don't have too much time to talk about, but the idea there is that we have this primary structure that is structuring this competition, this primary institution that's structuring this competition. And these things together, this mini-max sort of setting, and also this institutional constraint is what's going to give structure to the rest of the talk. So that's the idea behind the adversarial case optimal stochastic intervention, where you have two parties that are vying against each other. And we're going to actually approximate a kind of Nash equilibrium by iterative optimization of A strategy and B strategy. A strategy is B strategy, and we're gonna ask, how can A do better? And then we're gonna ask, how can B do better? And we're gonna do this in an iterative way. If you're familiar with machine learning, it has a flavor of something, some of the reinforcement learning with adversarial kind of neural networks. It has a similar flavor to that, and we're still going to be able to propagate all relevant uncertainties through automatic differentiation and the delta method. There are a few computational kind of things that are happening behind the scenes. For example, some of the quantities that we're trying to target, we don't have we have to approximate certain expectations using Monte Carlo and optimize through that whole process. But through the tools that hopefully we'll have time actually to work through together, you'll be able to actually do this sort of thing as well in terms of automatic differentiation and delta method, which is required here for doing this sort of analysis. Without these tools, we wouldn't be able to make much progress. So there are some nuances to this, and I think I'm trying to be clear with everything. So we're about 40 minutes into this, but there are a few nuances, and one of the nuances is that we actually need 2 stages of competition so that we get interesting adversarial dynamics to play out. So if you're interested in game theory, this makes total sense to you. The idea here is that if party A and party B faced exactly the same constraints, they would just do the exact same thing if there's a globally optimal thing to do. So if there really is like a best strategy out there, and that best strategy involves certain kind of policies, the 2 parties will basically converge to that best policy. So to get parties differentiating themselves, you actually need these 2 stages of competition, like a primary system or some level of inter-party competition, and then intra-party competition. Otherwise, you get this global matching. So I think that's just an interesting tidbit or an interesting kind of connection with some of the things that's been discussed in game theory, but now being connected to experimental analysis, experimental design, and that's something we can talk about as well in the Q&A. So that's what we have here. And if there are no questions, I don't hear anyone jumping in, so I'm going.
Oh, Connor, 1 second. Sorry to interrupt. Somehow someone's mic is on. It has been moving stuff all along and all the noise. And if you hear this, can you please mute yourself, and or you are constantly moving, and turn on your mic and turn off your mic and mute yourself. Otherwise, and we are recording your noise in the background. It's a little bit distracting for our speaker. All right. Thank you all. And sorry, Connor, please go ahead. Yeah.
Yeah, no problem. Thank you for that. Yeah. So if there are no more questions, we're going to talk. So I've given you the big picture. So the big picture, where do we stand? We've talked about conjoint data, and we've talked about how important that is for studying things like how people respond to political candidates, or how people respond. I mean, if you're not maybe, I'm not sure quite the background of all of you, but if you're in maybe a business school or something like that, this could be relevant in the context of marketing research, where investigators want to know what makes an attractive product. It's also really relevant to that. So that was the problem we started with. And then we said, well, how do we analyze that data? And we talked about a few different ways that can be done. But then we said there are some limitations to those approaches. And one of the limitations is that everything's being computed in the sort of average case way. And then we said, well, let's look at everything together in some sort of joint strategy. But then we said that strategy has to take into account both one party and the other party, both one actor and the other actor, both one country and the opposing country. And then we said, let's come up with a way of incorporating competition into our analysis of the conjoint data, of the variance-constrained optimal stochastic intervention. And then we said, we need some tools for that. And then we said, we're going to talk about that in the tutorial part. But this is where we've gotten to. And hopefully you're following along. If you're not, interject with questions, or we can talk about them in the Q&A. And if the details, details really aren't important. I think what's important is the big picture, and then the details will gradually get filled in. So this is the first thing that we'll discuss, but we do have in the paper simulations and other things along those lines. If there's time, I'm happy to talk through those things, since I think simulation, especially if you're interested in going on into academic research, can be a really valuable tool, and it could be helpful for some of you maybe to see how that plays out in this context where we're working with that high dimensional data. But that's going to be for the end if we have time. What I wanted to share with you is really just the application of these methods in practice, the application of these methods to better understand U.S. vote choice for president. But this, we could apply these methods that we've been developing not only for U.S. vote choice, but for other sort of elections as well, or for other sort of settings as well, beyond politics, which we can talk about in the Q&A. So the data that we're going to use is this Ono and Burden experiment that was designed to study the effect of gender on vote choice. And the design here was a forced choice conjoint. Basically, respondents were given two candidates, candidate A and candidate B, and they were asked, which candidate would you vote for? This one or that one? Or which one would you choose? The candidate features were randomized in just the exact same way that we were talking about at the very beginning. And the sort of features that were randomized, in other words, the factors were things like policy position, gender, race, experience, party, all these other things were included in this experiment. So the original experiment focused on the gender AMCE. Remember, that stands for average marginal component effect. That was what the original paper did. But what we're going to do is we're going to probe something a little bit different. We're going to ask different questions. And one of the questions is, what would the optimal strategies be for different groups of people? For example, all voters, Democratic voters, Republican voters, across all the features, not just gender. We're also going to ask and compare the average stochastic intervention. Remember, that's just like the strategy in that average case, which is sort of the baseline, and then the adversarial case, which is what I think provides a particularly useful sort of approach. So we're going to compare those two approaches. We're going to see what we learn, and we're going to see if one of these approaches gives us a more realistic understanding than the other. And we're going to actually be able to quantify that, and that I hope will be informative. So we're first going to show you some results on the optimized expected outcome in the different cases. So the thing that we're going to look at here is the expected optimal Democratic vote share under that strategy that we've discovered, and we're going to compare that against the average marginal component effects. And so the idea here is, let's look at Democrats optimizing against an average case opponent. That basically means the opponent is not optimizing. The Democratic candidate is optimizing, but the opponent candidate is not. That's what's being covered here. And we see something that looks like this. So the idea here is this Q hat of pi hat star. This is the expected Democratic vote share under this particular way of allocating the treatments. There's about an 80% vote share here in this case with confidence bands and everything. And this compares, favorably against all of the different average marginal component effects. So this is what we get with the analysis in this average case. But you might be asking yourself, and I'm sure you're asking yourself this question, well, we're getting an estimated optimal vote share of 0.8 of 80% of voters, but I don't see that happening in the political realm. Like, usually elections are a lot closer than that. And the reason why we see this divergence between what we're estimating here with what we see in reality is that this sort of analysis alone, it's not incorporating the adversarial dynamics that we've been focusing so much on today. The dynamics that make politics politics. So what we're going to do now is we're going to compare the expected Democratic vote share, not in the average case, but in the adversarial case, and we're going to say, what about a Democrat optimizing against an adversarial opponent? And this will be our question of interest. And now we see the results shift dramatically. No longer do we get 80% vote share as something that's attainable. Now we get a vote share much closer to 52, 51, 52% with this confidence band going past 0 or going past 0.5, indicating that in this case, the results look much more in line with historical experience. We can see that by looking at observed data from real elections. So what we've done here is we've gotten the winning two-party vote share for the real elections, and we plotted them together with our estimates for the optimal vote share under these strategies. And we see that in the average case, the result looks far outside of historical experience. That's what we see up top. Whereas in the adversarial case, that estimate is much closer to what we actually see in the real world of politics, which we think is important for reasons which we can continue to discuss. So now these were the average outcomes under those different strategies. So the last thing that I'll share with you before I conclude and then maybe Q&A and tutorial. The last thing that we're going to talk about is a preview of the strategies themselves. What I showed you before, that was just the average vote share, essentially, under the different strategies. But you might be asking yourself, what are the strategies themselves? And there are admittedly going to be a lot of results that I'm going to throw at you. So I wanted to summarize things before I threw the results at you. And the idea here, like the big picture, is that the adversarial case strategies qualitatively resonate with historical experience over and above the average case strategy. So that's just the takeaway. And I'm giving you the takeaway before I show you the results, because there are a lot of things to look at, and it might feel a little overwhelming at first, but I promise you every point is something that we can understand together. So this is the big picture takeaway. I have some examples here. So in the average case, the Republicans should upweigh black female candidates so as to increase their vote share, but we don't see, candidates like that being emphasized as much as other sorts of candidates. And in the adversarial case, we see other kinds of candidates who are more typically represented within the Republican leadership being upweighed in the adversarial case. And the idea there is that the primary competition dramatically changes the kind of strategies that are being inferred from the conjoint data and from the data analytic tools that we're using together. So that's like the takeaway here. And this is these are what the strategies look like. So every point here, it's not an average marginal component effect. Every point here is a probability under the new strategy of assigning a feature like this. So in this case, this is these are the results for the Democrats in the average case. So we have these are all the probabilities, and we have so let's just look at the top column. So this is sex. We have male and female candidates, and according to this average case analysis, male candidates should be upweighed. The probability of assigning a male feature should be upweighed compared to female, and that's why you see this point here towards 1. And we've done this for all of the other features in the experiment. Age, family, race, experience, personality, party, competition, etc., etc., etc. And we've done this analysis with all of them. We've gotten the new kind of probabilities, which represent the strategies for all of the different features. And this is something that we've done. And we see that Democrats in this case should, so this is what we see in the average case. And we can do this analysis not only among all voters. So these are the results for all voters. Not only for all voters, we can also do the results for different kinds of voters. So these are the results for the Democratic candidates, or for Democratic respondents. And these are results for Republican respondents, and these are results for independent respondents. So we can actually infer a different strategy for these different subgroups and compare them and contrast them. Where are they similar? Where are they different? So this is it's almost like a recipe book for what sort of policy positions would gain support among different subgroups. And this is important for summarizing the kind of things that voters respond to. So that was the average case, and there were a few things that were a little bit strange, like, for example, the Republican strategy upweighing certain things that we just don't see very often among Republican candidates. And this led to the question of why is that? And the answer is really this notion of strategic competition. So now we have the Republican and the Democrat strategies for this adversarial case analysis where things look very different, and the results actually seem to corroborate what we observe based on observed strategic behavior a little bit more. So these are the strategies from the adversarial case. We could maybe in Q&A kind of do a deep dive with some of these, and I'll summarize the results a little bit later on as well. But big picture, one of the wonderful things of framing the approach in the way that we framed it is that we can compute we have a strategy, and a strategy is embodied in a probability distribution. So if you're familiar with probability theory, what we can do is we can take that probability distribution and look at how likely different things would be under these different distributions. So we have the average case and the adversarial case sort of analysis. And what we're going to do is we're going to compute the log probability of seeing real world political candidates under these different strategies. So these log probabilities are log probabilities from real candidates in real elections. And we see that in the average case, the log probabilities are lower than in the adversarial case. That means, big picture takeaway, that means with the strategies inferred in this adversarial arrangement, we're getting strategies that are more in line with historical experience, more in line with observed behavior, which I think is important for practice. So implication for practice, this proposed approach is going to allow us to compare the strategic behavior that is actually occurring with the observed optimal, and we'll be able to see when someone's operating in a strategic way versus when someone's operating in a less strategic way, or when groups are operating in more or less strategic way. So I've talked for about an hour at this point, so I want to wrap up. So here are some conclusions from this analysis. Conclusion number one, when we incorporate adversarial dynamics and when we integrate this analysis in with the conjoint data, we find that neither Republicans nor Democrats hold a decisive advantage electorally in equilibrium using the tools that we're discussing here. We also see that there's policy matching and deviation. In other words, Republicans and Democrats policy match on some issues in these strategies that we've been learning, but they deviate on other issues. And here are some examples listed for you as well. And I think one interesting open question is the systematic analysis of how competition, the adversarial component, actually increases the variance. In other words, how does competition increase the variance of the outcomes we see politically? And this is something that we are definitely eager to explore as well. So just to conclude, the social world, the natural world, the political world, this is a competitive space. This is a high dimensional space as well. And the statistical summaries that we're working with are often unidimensional, looking at one thing at a time, and they often can be static. In other words, not incorporating the strategic dimension. So what we've been trying to do in this work is to provide a gateway to more holistic, but still interpretable, still understandable summaries of these complex effects and interactions, while also incorporating these competitive dynamics that we've been discussing. So I think there are a lot of open questions in terms of multiple players. Like what happens in the setting where you don't just have one party, but you have multiple parties, or one player, or not just two players, but more than two players. So this could be really relevant for different sorts of electoral systems where there are not just two major parties, but additional major parties. Could also be very relevant to international relations where the number of players in these sort of international relations settings is not just two, but actually potentially many more than two. So we have those open questions among others. For more information, here's a link, and I have some tutorial in the next part of the discussion, but I want to maybe stop here and maybe now we can do questions. The tutorial, I'm happy to send these slides along as well. It's more practical in case we had time to get into the details about some of these things and trying to empower you, as students and others to learn these tools and work with them in practice. But let me stop here for questions and for discussion, and then we'll go on to the tutorial if there's time.
All right, thank you, Connor. And we have a question, I think, a comment here, and by students is saying that marketing research examples, and I think you mentioned about using Conjoint a lot, and so basically looking at new card configurations and feature combinations. I think that is the traditional Conjoint setup, and now you introduce this method, allowing to do finding the optimal combination when you do all these features, and you don't have to worry about whether they are correlated, and you can do some new methods to find that optima. And can you also think about this in the marketing setup? Before then, do you use a lavalier mic somehow, and I think somehow your mic may generate some background noise, and maybe your mic is the culprit. Do you know? And yeah.
Maybe it's me. I'll try not to move. Maybe it is. Is it?
Oh, the mic. Okay, the mic moves with you. Okay, peace and oh yeah, go ahead.
I'll try not to move. I'll be totally still for you all. But apologies for that. You know, it's a great question. So in the context of marketing research, I guess I would say a few different things. First of all, I think the sort of approach that we're trying to build here could be very relevant. And I think there are a lot of experiments done in marketing research. So some colleagues here at UT Austin are actually in the business school doing causal inference and doing experiments to learn about the kind of like feature aspects that potential buyers respond to. Or for example, on website design, you know, what website layout resonates best with the user. You know, is it this way, is it that way? There are all these different ways of aligning a website, as you know, in terms of color, in terms of how dynamic it is, in terms of all these other aspects to it. And the kind of optimization that we're working with here could readily be done in those sort of settings where your objective is to, you know, improve outcomes in the marketing or business context. The adversarial component would probably be a bit less relevant there, insofar as in the marketing context, usually, I mean, I suppose it could be relevant insofar as one sort of product is being analyzed against another product. So for example, someone goes into the grocery store to buy peanut butter, and some of the peanut butter looks like this and some of the peanut butter looks like that. They have different ingredients, they have different labelings, and in that sense there could be an adversarial component to the analysis, but I don't think that's been done. Our examples definitely haven't spoken to that, but maybe if you have an example, definitely feel free to shoot me an email as well, and we can take a further look. But it's a good question, and those would be a few thoughts. Other questions, other thoughts?
Okay, Mike. Okay, Connor, Dr.
Yes.
Here's I think I'm not sure if it's relevant, but from the audience, the question about, is there a better way or the logical adjustment for respondents' ability to differentiate the features of a profile? Maybe it's other than the topics that you're talking about, but can you have a quick response to that?
Yeah. Can you say the first part again? Is there a way to distinguish or to understand what a respondent is paying more attention to? Is that the question?
There are different features of a profile, and then some critics about respondents. I mean, for anyone who wants to differentiate or try to weight the different features for respondents, and then maybe they try to come up with to how do I say that, different features, they have different weight, right? But how can anyone be more so rationally to calculate different weight of each feature? I think the question confirms that kind of thing, and can we just adjust that? Otherwise, it could be just average or or impression of certain thing, certain candidate of a profile.
Yeah. Okay.
Um,
Yeah. Great question. So the question, I think, is getting at this notion of which features matter and which features don't matter. So we can do that in a few different ways. We can see that in a few different ways. So what's a good example of that? So So one example of that would be, so one thought for you, I guess the approach that we talked about here involves a two-step process where we're first modeling the outcome, and then we're trying to basically infer certain consequences of that model in light of the data. And in this modeling context, not all of the features are going to be weighted equally. So the favorability is going to be affected more by some things and less by others, and that will have an implication for the optimal that we'll be looking at. So in this case, we're doing a little bit of regularization also in the outcome model. So we see here that this personality, all the new probabilities for personality are all just the same value as the data generated probability. And the idea there is that respondents actually don't really care whether someone's honest or compassionate, at least in the data here as analyzed it. There's not really responsiveness to voters along those traits. So as a result, we see that the new counterfactual distribution is actually the same as the old one, and this is due to the regularization we talked about, as well as the fact that there's no response in the there's no response in the outcome model to these sort of features. So that's one way of how we're actually what we're doing here, incorporating the fact that the respondents care more about some things and less about others. For example, the respondents care a lot about security. They care a lot about abortion, immigration, but they don't really care much about personality. So whether the candidate in the setting is compassionate or honest, intelligent, in terms of personality type, that's just it's not really that important. So we're accounting for that fact. But there's a deeper question to what you've been. There's a deeper question though, which is when you're designing your conjoint experiment, how many features do you include? Do you include just two factors like sex and age and family, or do you include more, 5, 10? At a certain point, the respondents are going to they're not going to be able to process all the information about all the different attributes of the these candidates. So my sense is that there is a sweet spot in terms of how much richness we want in terms of numbers of features versus how much we want to, in a sense, overburden. How much we want to avoid overburdening the respondents by not having to incorporate too much information at once. And I know there's recent work on measurement error and conjoint designs, which speaks to some of these issues as well. So I think you raise good questions, a bit of information about how we adjust and try to deal with that in the context of the analysis discussed here. Yeah, great questions. Other thoughts, other questions?
I have a couple more questions, and can you hear me? Yeah, sorry, I was talking while I was mute, and my original question was, in machine learning context, we actually can create Shapley values to attribute the probability contribution to each candidate or which attribute or each feature, regardless whether they are orthogonal. And so that is only looking at the way they can contribute to the probability or prediction. So say the whole model, the combination, I predict 89%. So I can attribute, for example, this the top candidate being 20% coming from a party ID, 15% coming from maybe an issue, maybe from other demographic variables, etc. So that method is more generally looking at the prediction, but providing some interpretable results. But we still do not. But your method is directly addressing the high dimensional space, and instead of looking at just the probability contribution. So this picture, this slide is particularly interesting, for example, and this is exactly showing that, and such a decision could be high dimensional, and in this case, and personality is basically no indifferent, right? So personality has nothing to do, and with to do the to get intervention with maybe vis-a-vis other variables like gender and also issues. So do you want to compare these kind of methods? And is this something you believe that machine learning models will finally get some more interpretability using this approach?
Yeah, no, it's an interesting thought. So I think we haven't done a direct comparison with something like shapely values or other sort of summaries. I think one of the motivations for doing this, as you mentioned, to get some sort of interpretable output from the model. So, in other
Yeah.
words, have some super complex model for
Yes. Yeah.
yeah, that model. Like, how do we summarize it? And the shapely values might be one way, the coefficients might be one way, but the approach here is, I think, nice because it is interpretable. There's a probabilistic interpretation. We can incorporate a lot of different dynamics. So I guess I would just agree with you that there is a connection and that it's an interesting one. And we can think a little bit about how might that be done in the paper or what might be done in the paper. And just the last point on that, something like a shapely value, it's a bit harder to sort of see how that's real data in terms of, that's one of the nice things about what we're doing with these distributions. We can apply data to these distributions and they give us a probability.
Yeah.
Yeah.
Can you go back to previous slides on the personality one and adversarial case? So you can see the personality is basically nothing. And can you give a little more comparison? Say even the expertise, and you can see a lot of indifference. And can you interpret further on that only on certain policies, right?
Yeah, exactly. So certain policies, so the idea here, so just to reiterate, there's a dashed line here in these figures. That dash represents the data generating probability. So when these points are from the dashed line, that means that the strategy that we've inferred, it deviates a lot from the original data generating distribution. But when it's the same, that means the strategy doesn't differ. So what we're getting at,
yeah.
so certain things that are far from those dashed lines and certain things that are close. The fact that all these dashed lines are at the same level, that's because we've uniformly, or the original experimenters have uniformly allocated the treatments. In other words, all the different possibilities were given with the same probability. So in this case, it just, given the data that we have, it turns out that, incorporating all these other factors together, the voters, the respondents, are not choosing one candidate over another, seemingly on the basis of things like these personality characteristics or the interaction between these personality characteristics and other things. So in the model, in the output model that we specified, we have main terms and we have interaction terms. So if we see everything basically at the data generating probability, that basically is telling us that personality isn't really affecting the choice probability, even if we interact it with all these other things like immigration or spending or abortion or race. So that's what this is telling us. It's telling us that personality and the interactions of personality with all these other things isn't affecting the outcome. Therefore, the strategy everything's just going to be set at the data generating probability. Yeah, good question.
Yeah, great. Any more questions from the US side or Taiwan side? And how computationally expensive it is, Connor? Looks like there's a lot of
Yeah, good question. So we spent a lot of effort on the computational side. And like I said, I'm happy to send these slides since there is a little bit of discussion on computation. But big picture, the adversarial case analysis is by far the slowest of all the complexities we've discussed. The other cases can be finished in around, it's about a 5-minute process. The adversarial case is more like a 10 or 15-minute process. So it's not hours, it's not days, it's on the order of minutes. It can't even be faster if the data are particularly large. That's a bit. Should I talk about the tutorial, or we can keep with questions too? I'm not sure how practical the group is in terms of coding and stuff like that.
We could be we have we could have a diverse group though. Yeah, but I saw you have another 90 slides, and I would love to go for another 2 hours to learn line by line the codes. And but let me check with Peter first, and see how the Taiwan side will ready for a little more tutorial hands-on. Peter.
Can you hear me now?
Yes, I can.
Oh,
I
yes.
can hear you.
Okay.
Yeah, thank you.
So, yeah, why don't we just go ahead, and I think we're go already. Go to the tutorial a little bit.
Okay, sounds good. Yeah, so I thought it would be good to talk about this since, some of you might have coding backgrounds, some of you might not. But through these slides, which I'm happy to send you away, it'll give you a recipe book for using the tools that we've used in this project for building the software that underlies all the results that we talked about today. So it's one thing to have an idea, but it's another thing to implement that idea in practice. And in your careers, learning the best computational tools will be potentially important in terms of allowing you to do things that are difficult for other people, sort of giving you a leg up in that way, empowering you in that way. So I wanted to talk a little bit about the tools that we used in an effort to try to give you this knowledge so that you can use it potentially in your own work or in your consulting projects or business related or policy related endeavors. So that's the tutorials. This should take around 20 minutes, then maybe we can have another Q&A, and then maybe we can go from there. But what we do here is we basically talk about why we needed to use these tools, and then we talk about how you can actually use them in R and how you can implement them. And I've tried to be kind of as clear as possible, working from the foundations on up. So I won't dwell on this because I think people kind of get the message, but the basic point is that we have computational needs. So what we were just describing involves optimizing complex objective functions, and it involves getting something that we call the Jacobian, which we need for the delta method. So that's just something that I'll break down very simply in a minute. So the basic idea is that in order to optimize this complex objective function, we need to use an iterative approach to doing so. I'm not going to go through the details now. Here are the details listed, but the key thing, and I'm happy to go through this maybe in the Q&A if people want, but the important thing is that we use something called automatic differentiation to get what are called gradients to do this optimization. So the basic idea is we're going to start with our initial guesses for the parameters, and then we're going to ask ourselves, how could we move the parameters so as to best increase our objective function if we're trying to maximize something? And then we basically tweak the parameter estimate so as to account for that information. This approach is known as gradient ascent. And to get these gradients, which basically tells us the direction which would most increase our objective function, we use a tool called automatic differentiation. And I'm going to work through with you how you actually can use that in your own work in just 1 or 2 lines of code that will hopefully help empower you in your own research. So this tool called automatic differentiation, it's an algorithmic tool for computing the gradients of things that might be hard to derive analytically. So you might remember from your math classes, chain rule, differentiation, et cetera, et cetera. We're actually going to do that exact same process of tracking all the operations our code is executing and we're going to compute the derivative of the whole entire function using the chain rule to basically tell us how everything relates to everything else, so that we can, in algorithmic fashion, compute exactly the gradient of a really complex function. Even if we can't write down what that formula is for the gradient, we can still compute it using these computational tools. So this is the first need that we need to meet. But there's a second need that we need to meet as well, and that's basically even more complex generalizations of gradients to multidimensional inputs and outputs. The details really aren't important. I know some of you might have a statistics background, some of you might not have a statistics background, but just for those of you who don't, the basic idea here is that in order to understand the variance of those optimal policies, we need to understand how one thing relates to another in a more multidimensional way, in a kind of more holistic way. So I have on this slide a few of the details behind that, but the basic idea is we're actually generalizing gradients to an even multidimensional space where the output of the function that we're differentiating is actually multidimensional itself. So the input is multidimensional and the output is multidimensional, and this is important for computing the Jacobian matrix. It's called Jacobian matrix, which is subsequently important for computing the variance covariance matrix of our estimates, which is subsequently important for getting confidence intervals. So big picture, this is important for getting confidence intervals, and this might be really hard for me to do without a computational tool like the one that I'm going to talk to you about in just a minute. And in particular, the tool that we're going to use is going to be available to you within R. I'm not sure if R or Stata or other computational tools are really your focus. I know a lot of social scientists do use R, so I'm hoping that some of you use it too, just so that we're on the same playing field. But the things that we'll discuss now, I know will have an analog in tools like Stata. The notation might be a little bit different, but what we're going to talk a little bit about is how to combine R with Python. R is really nice because a lot of us might know R, but Python is really nice because it's widely used within the machine learning community. It has great support for that tool I just talked about, automatic differentiation, and it can be optimized in a really efficient way to make our code fast. So if we didn't use these tools to do what we did in this project, instead of taking 5 minutes, might take us, 5 months. It would just take a lot longer. So we're going to optimize to the nth degree. So I'm just going to, in the next few slides, if you permit me, just talk a little bit about how to integrate R with Python to emphasize to you that in the current state of affairs, I think we're getting beyond the point where we think of ourselves as, oh, I'm an R user, or oh, I'm a Python user. We're getting to the point where a lot of these computational tools, Stata in Python, R in Python, a lot of these tools can actually be harmonized together, and we're actually going to use Python within R 100%. We're not going to leave R. We're going to stay within R. We're going to use Python tools through a package called Reticulate, and we're going to be able to actually write what in the computer science world we call backend, like using R together with some of these other libraries, so that we can be empowered to do analyses that might otherwise be more challenging and just take a long time. And it's used by the package that we built for the discussion that we're going through today, for the tools that we're discussing today. So I know I don't want to run on too long with this, and I want to make sure there's time for any additional questions. So I'll just give you a flavor of it, and I won't dwell on details to any great extent, since I know some of you might not have the same background as others when it comes to the coding and everything. But in case some of you are interested, I have the slides here about how you would actually set this up on your computer. And some of you might have used R packages before. So this is basically loading into your environment the Reticulate R package, and then you're setting up a computational environment using this line of code, and then you're going to import Python libraries right into R using this code here. You're importing in a package called JAX, and then you're importing in a package called Oryx, And then I've given on the bottom tools or code for how you actually might install these packages on your own computer. These work no matter whether you're on Linux, Windows, or a Macintosh. They'll still all work the same. There might be some differences, but they'll still all work the same. I should say this code here, this use conda and env, this is going to be specific to your computer, and I'm happy to talk offline with you how exactly you set this thing up. But all the rest of the code will be exactly the same. And now you can see here that you can write JAX code. So JAX is a tool put out by Google, which is a very optimized set of tools for doing linear algebra. So things that we're doing in this paper. So it's optimized for that, and it also has really great support for that automatic differentiation that I was emphasizing is something that was really important. And one of the things that it can do is we can do things like matrix multiplication. So I've written an R function here that does matrix multiplication between A and B, and it uses that JAX backend that I was talking about, JNP, that stands for JAX NumPy. So I'm using the JAX backend to do this matrix multiplication 100% from within R, which is very cool. We don't have to go to Python to do it. We don't have to learn Python to do it. We can actually do it within R, and this is what we've done here. The other thing that I wanted to just mention is that these libraries, they enable and allow something called just-in-time compilation. So the idea here is that we have this matrix multiplication function, and we want actually to make it even more efficient. And we can make it even more efficient by compiling it to get a really optimized representation of that computation. So this JIT basically takes the function and it finds a really efficient way to run that function. The details aren't important for now. What is important is the goal, the motivation. And the goal, the motivation is to take a function that might have redundancies, that might be inefficient in some way, and to optimize it as much as it can be optimized. So this is how you would do that. And there's some details here about what exactly this just-in-time compilation refers to, but we'll show you later on how this can speed things up by a huge amount. So I have some calculations done here. If you want, you can play around with this offline, but there are two important points. Important point number one, this is R, and we're doing JAX calculations from within R. And that's going to hopefully empower you to do the same thing. The other thing to mention is that
Connor,
yeah.
I take it back, and I think one thing you want to make sure the student is using it in R Studio, and otherwise you can do it in R, but you have to deal with the multiple interpreters because different computers may have installed different Pythons in the backend. And for example, and in my case, I use Anaconda, which is slightly different than the Anaconda used in R. And then, so by far, I think you are referring to using in R Studio, right? Then you have a choice of interpreter. And will be some students in case they have multiple setups and of Python. Yeah. Are you using R Studio?
R Studio. And this could be, this may have been just talked about by others or other parts of the class. Maybe this is review, in which case I hope it's helpful. But yeah, R Studio, everything I've said up till now, when I say R, I mean R used through R Studio.
Yeah. Okay, good.
Yeah, good clarification. And what you were talking about regarding Anaconda environments, that's where these three lines of code come in. You might have different environments for different Python versions and things like that. You can tell R which version to look for using the code listed here. And this is just the version. This is the Conda environment where my libraries live in. It's just this one listed out here. For you, it might be different. Great points. Yeah, no, super helpful. Very good. So I just wanted to emphasize a few different things. 20 minutes or so until we should be done. So the first thing I'll emphasize is just how there can be really massive speedups relative to base R. So what I've done in the top code, what is important is the bottom part. So I've written an R function I've written R code here for doing matrix multiplication. But I do the same thing with this JAX backend that we've been talking a little bit about, both with and without this just-in-time relation. On top of in terms of execution time. So instead of taking 20 seconds to run through all this code, matrix multiplication, now it's 1. And this is a big speed up, which can make a big difference, especially as we grow our projects in complexity. So this is another example. This is one example that's giving you experience with it, and also just showing you that it's actually simpler than it may seem if you don't have experience using this sort of approach. It takes a little bit of time to get used to the semantics, but if you work at it and if you read the documentation, usually things will become clear. The only difference with Python, if you were actually in Python, this $sign would be replaced by a dot. But in R, the dots are replaced by $signs. So there's a bit of semantic difference. Not really. Then so I have a few other thoughts about auto differentiation. So remember that auto differentiation was really important for doing the optimization through what we call gradient ascent, but it was also really important for getting that Jacobian matrix of how one thing relates to everything else in that delta method setting. And we use automatic differentiation actually in both those two cases. And we've actually written here a function that takes this matrix multiplication output and then just sums it up. And this is my function. And what we're going to do now is auto differentiate to get the derivative of this function with respect to A, and then the derivative of this function with respect to B. In some cases, you might be able to do that analytically using your knowledge of calculus. But in a lot of other cases, you might not be able to or might not want to get the gradients of some really complex function that you use that algorithmic tool for representation of the gradients. Actually, simple. So we take this function, and now we apply. We feed this function JAX fxn. We feed this function into this JAX gradient function. We specify what arguments we want to differentiate with respect to. And here we're differentiating with respect to the first and the second argument. Python, just a word of caution, everything in Python is 0 indexed. So to refer to the first and second position, we refer to 0 and 1 respectively, not 1 and 2. We refer to 0 and 1. So what we're doing in this line here that I've highlighted is we're computing the gradient of this function with respect to the first position and the second position, and then we're compiling that function. And the beautiful thing is we're doing this all in R. And now we've evaluated that function here in the next line of code using the array A and the array B, which is basically just a matrix which has been fed into the JAX backend, and we call it. And now we can access the gradient of the function with respect to A and the gradient of the function with respect to B. And it was extremely fast and extremely efficient. And the code actually was very simple in order to get this. And this is something that you might be interested in doing in your own work, maybe for building a library that solves some of the problems that you're working on in a really efficient way. So I have 1 or 2 more slides on this, just if folks are interested. I wanted to talk briefly just about using random sampling with JAX. So random sampling can be really useful for simulation and other sorts of things. And I have here code for doing this sort of random sampling within JAX. I don't think, just because we don't have that much time, I don't need to dwell on the details here. What the one thing that is important is you have to specify a seed for every operation. In R, you just set seed at the beginning of your R session, and the seed is set throughout, and and that's what happens there. With JAX, actually every random sampling operation has to have a unique key associated with it. So think of it like setting the seed for every single random draw. it's a little bit. But we can optimize the random sampling process using the compilation that I was just talking to you about, and the speed ups here are a bit more dramatic. So when we compile the function versus when we don't compile the function, it takes the time from 2 seconds to 0.00. So this is a dramatic speed, and this can be really, really powerful in your own projects. And maybe the other takeaway is just the linear algebra, the representation of arrays is so efficient with backends like this that multiplying the problem by 1,000 sometimes only leads to a 10-fold increase in computation time. So we basically did what we did up here, but down here we multiplied everything by 1,000, and now is the additional time that it takes when we compile everything is only about less than 10 times greater. So the idea here is we have efficient representation of bigger quantities, so we can often get a big benefit of speed at a relatively little cost, and that the cost is cognitive in terms of learning these tools, but that will be reduced with time, and the other cost is just a bit of a cost in terms of learning to install JAX as well. So these are just a few things about how you might use backends like this in your own work, and a little bit on using random sampling with these sort of tools, a little bit on using automatic differentiation with these tools, as well as using the compiler, the just-in-time compiler. And we saw together how it's really not anything rocket science. Like, this is a tool that's used by machine learning researchers, but there's no reason why it can't be used by you in your own work. And this is giving you very concrete examples of how you can do that. And there's more material online as well, but this is just the start of the discussion, really. So I think that's basically what I have for the tutorial part. I have additional information. I could talk more about the simulations and about other things like that, but maybe I should pause just to ask if people have any questions, or if they want any additional thoughts or perspectives on the coding side or the tutorial side. I'm happy to field any questions about this as well.
Any questions? I think this is very interesting way of applying some machine learning techniques when we come up to a conjoint setup like that. And this is the first time I see this. Particularly look at it, that you have a high dimensional space, and in that kind of combinations, that is neat. And actually, you can even think of more applications. And yeah, never tried that. And we should factor in our new curriculums in other courses too. And currently, we are still primarily on R environment, and we have R and Python, and now we should more. This is a great example to demonstrate, and you can do both and take advantage of each, and great features like Python. Never use Jazz, and I use Articulate quite often. But this is a wonderful way of applying these techniques to modeling. Yeah. Any questions from Taiwan side or from the US side?
So students are wondering if the sample code can be shared, and like I checked your website and there's some codes, right, Connor? And
Yes. So
the question is about just try this at home and then play around by themselves.
Yes, that's a great question. I can send you a script that goes through all of it, and that's fine. So if you're happy to go, my website is primarily related to packages. Coder, you can go to that of Jack's backend. Take a look at that. But I'll definitely send this code because it's a good, hopefully, introduction. And I would, be great function in a logical way. Five, can't stay awake any longer in the morning, but very. Yeah,
Okay.
Yeah, just one thought. When if you have a, just maybe my personal perspective for the students, I think it makes sense to concentrate in one, learning one coding platform really well. So in this case, learning R really well, and then bringing in Python when needed through Reticulate. Since there's just a big cognitive cost to going from one to the other, whereas this integration can be a lot more efficient cognitively. So that's just one thought as well for those of you who are.
Totally agree. Yeah, we are working in that direction now. We're making sure the students are multilingual too, multilingual fluency. Yeah.
So that's that. Otherwise, other questions about code or the paper or anything along those?
Anyone? All right, and shall we wrap up here? And now, Connor, and are you going to post these slides to your website, or you can send a copy to me, or I can have Peter post it on our web. Now, first thing first, do you mind posting this to the public, or you will want it only to our students? And
yeah,
what do you think?
Yeah, so let me talk to my collaborator, Coach on the project. I think.
Yeah, Professor Imai. Yeah.
So definitely, eventually, it will be okay to post publicly. We might want a version of the paper posted publicly, or if that would be okay. But let me confirm with him.
Sure. Yeah. Otherwise, we will just do it internally and only upon request, but not put it on the website. And I think it's understandable. And please just let us know, or just send us the copy that you feel ready to be disseminated among us. I mean ACSU and also UTT only. Then maybe sometime in future you want to send a public version, and or maybe we refer to your website for another version, a more fuller version, and that will do. But let us know what your decisions are, and including with I think Kosoki, right, and Professor Yima may have his own opinion too. Just let us know how would you like that to be disseminated. All right.
It sounds good. Thank you.
Right.
Thank
We
you.
have the audience all registered, so maybe we can just if you may, then we can send them to our audience today. Yeah.
Yes, that sounds good.
Mm.
Okay. So we conclude here. I think thank you very much. This is late, and I think this is really informative, and particularly eye-opening part on the computational part. And yeah, I really appreciate it. And all right, thank you. I think also be reminded we will have another special presentation next week, and maybe before you go register and on our website at dacolloquium.com. So that will be we will have it consecutively for 6 weeks, and this is the second week. And please don't miss the chance to register for next week. And now we have Professor Sperling and doing embedded regression, and I think that will be another wonderful presentation too. All right. Hopefully we cross path soon, Connor. Okay. And
when I'm up there.
all right.
Yep, thank you all, and have a good night.
Thank you all. Thank you.
Good night. Good night. Thank you, Connor. Thank you. All right. I think